All right, guys, here is a couple of notes that I wanted to add. I will include these in the module as well. However, I wanted to put them as a slight review in case you wanted to look at them in this video. These are the ions, in addition to the ones listed in your book, that I want you to pay attention to as far as the ones that have multiple charges. This also tells you the traditional or common method of naming them. This is kind of, I suppose you could say, this is old school. And then if that's the case, then this is the new or systematic method of naming these ions. It's important to know the common or old school method of naming them because you'll still see these utilized in the world out and about. However, the systematic naming is the one that we're really trying to make sure that you guys know, and the systematic naming method is the one that you will be most tested on. As you can see, these correspond with these particular ions. One of the ones that I wanted to draw some attention to is to pay careful attention to mercury, because if you look carefully at mercury, the difference between mercury 2 and mercury 1 is that mercury 1 actually has a subscript of 2, meaning that per atom in that dimer, if you will, is one positive charge on each mercury atom. However, they dimerize, and therefore it is listed as Hg subscript 2, 2 plus. Okay, aside from that, let's move on. Here's a list of some of the most common polyatomic ions that you should know. This again will also be listed in addition to a few other resources. There's only one on here that I noticed was not listed that I do want you to know, which is called bisphosphate, or another name for it is diphosphate. Sorry, it should be called dihydrogen phosphate. So it's either bisphosphate or dihydrogen phosphate. And this one is H2PO4 minus. As you can see, it's related to this one, hydrogen phosphate, and of course, phosphate itself. Pay attention to the charges here since they didn't actually put it on there. In fact, just to make this a little bit more straightforward, I'm going to put all of these the appropriate charge. You can see here, these are all 1 minus charge. And since the 1 would be redundant, we simply put a single negative sign as a superscript to indicate that negative charge. You can see all the families we talked about in the previous lecture, including some others. Here we've got, this should be 1 minus, this should be 1 plus, this should be 2 minus, and this should be 3 minus. Carbonate, of course, 2 minus, chromate, 2 minus, dichromate, 2 minus, even though it's got Cr2O7, still 2 minus. Hydrogen phosphate, 2 minus, oxalate, 2 minus, peroxide, 2 minus, sulfate, 2 minus, sulfite, 2 minus, tartrate, 2 minus, and thiosulfate, 2 minus. And then finally, we come over here, arsenate, 3 minus, borate, 3 minus, phosphate, 3 minus, and phosphite, 3 minus. Okay, now, one of the most important things from this chapter that you will learn is how to name ionic compounds. And of course, from a name, how to write ionic compound formula units. Now, as far as naming compounds goes, we can break this down in a number of ways. We'll say that there's kind of type 1. And I think your book breaks it down in this fashion. Type 1 are monoatomic or polyatomic ionic compounds with no we'll have fun here. We'll put with no wacky transition metals, those metals that have the possibility of two or more possible charges. So the way you name these are the name of the cation without the word ion, followed by the name of the anion, of course, without the word ion. So for example, if you see HCl, there are multiple names for this compound, but based on this naming system, we would call this hydrogen chloride. Okay. Now, if you saw something like Na2CO3, this would be sodium carbonate. If we saw something like NH4F, this would be then ammonium fluoride. There's a bunch of practice problems in the book as well as available for you guys, and I will post some extra practice problems as well. One thing I do want you to keep in mind with polyatomic ions in compounds, if there's a need for two or more ions in the formula unit, you put the ion in parentheses, followed by a subscript of the number of ions. Now, that does not affect the name. Subscripts for ionic compounds are not mentioned in the name. You ignore subscripts, numbers of ions, numbers of that element in ionic compounds. Okay. So, for example, when we write this compound, you can see that this is going to need a 3 because phosphate's charge is 3 minus and ammonium is 1 plus. This is still just going to be called ammonium phosphate. Okay. There's a whole bunch of examples that I could do, but it's more important that you get the practice rather than watching me do a whole bunch of things naming these. Now, the process of going from name to formula unit requires two things. One, you actually have to be able to decipher the name and know what ions are being mentioned in that name. And you need to remember what the symbol is with its charge. So you need to, one, be able to decipher the name into ions. And you need to then know what symbol or symbols, if it's a polyatomic ion, correspond to that name and what charge that ion has. Okay. Because if you see something like, say you saw the name calcium phosphate, you would need to know that calcium, using your periodic table, is a element that produces a 2+ cation, and phosphate is an ion that has 1 phosphorus, 4 oxygens, and a 3- charge. So that when you write the formula unit for this ionic compound, you would correctly write Ca3 parentheses PO4 2 in order to make sure that the charge is balanced. Okay. I haven't forgotten that I mentioned that there was a second type of naming of compounds. So type 2, as we might have said, is the ones that utilize transition multivalent cations. Okay. And if you recall, we had a list of ions in the previous lecture and in this one that we mentioned. So a couple of examples of those, of course, are, for example, iron has the possibility of being iron 2+ or iron 3+. Another example being mercury, and I, of course, enjoy looking at this one because it is such an interesting one. Mercury 1 is mercury subscript 2, 2+, and mercury 2 is simply mercury single particle. Well, they're both single particles, but single atom within this particle 2+. Now, when you look at compounds made of these, if it was utilizing your 2+ ion, then the name would be, of course, here it becomes iron 2 or mercury 2, followed by whatever anion is associated with it. If you are looking at your 3+ for iron, then it becomes iron 3, whatever anion. If you're looking at the 1+ for mercury, it becomes mercury 1, followed by whatever anion it is. Fairly straightforward naming method, but it's important to be able to delineate and specify this as appropriate. Now, how do you go back the other way from the name to the formula unit? Let's just do a few examples of this. Say you were given iron 2 carbonate. You would need to know that iron 2 is going to be Fe2+, and carbonate is CO3 2-. Therefore, your formula unit is going to be FeCO3. Say you had something like, if your name was mercury 1, we'll go with mercury 1 oxide. So mercury 1 is Hg2, 2+. Oxide is O2-, meaning that you have Hg2O to give you a neutral ionic compounds formula unit. Okay, we're going to stop this lecture here.